Hi, now that we have made the two first steps of our strategy, that that is deriving the Schrödinger equation using some method, in this case the stochastic method, and then relating this new method to the previous derivations, we may profit from a number of constructs, physical constructs, that derive directly from the notion of stochastic behavior. First, we need to present at least a vision of what would be the origin of the stochastic behavior. This video is devoted to this. Okay, our question, of course, is where do fluctuations come from? There are two possible answers for this question. We may assume that our system is an open system, or we may assume that our system is a closed system. If we assume that it is an open system, and in fact this is the usual assumption of stochastic derivations, we get an open system, of course, and generally what is assumed in these cases is that the atom, for instance, or the physical system, is immersed in an electromagnetic field which is usually connected to the background radiation field. So the system is open, and this is the usual interpretation when people working with the stochastic approach, physical systems, quantum mechanical systems. Of course, we cannot do that. In any part of our derivation, we assumed an external field for our equations. For instance, when we are considering the hydrogen atom, the potential is the potential relating the electromagnetic force or potential between the nucleus and the electron, and only that. So we cannot assume such an approach which assumes that the quantum mechanical systems are open. Instead, we must assume, using the present approach, that our system is closed, and what we have is only the hydrogen atom or the harmonic oscillator as a closed system. Then we must again pose the question, where do fluctuations come from in this case of a closed system? Okay, fluctuation in closed systems may happen if we consider two important statements that we may find in Kalin's book, in terms of statistics. This first one can be found in page 210, and says, the equilibrium state static from the viewpoint of classical thermodynamics is necessarily dynamic. Local inhomogeneities continually and spontaneously generate, only to be attenuated and dissipated. A second statement may be found in page 423 and says, the subsystem, and I would stress this word, it is very important for us. The subsystem may in fact be a small portion of a larger system, the remainder of the system constituting the reservoir. In that case, the fluctuations are local fluctuations within nominally homogeneous system. Okay, using these two statements, we may now focus into this notion of subsystems to find in what ways a closed physical system can show fluctuations. We may then look at our Schrödinger equation that describes our physical systems and try to find two subsystems. This is not hard. Look, for example, the hydrogen atom or any other atom, for instance. We may have a particle subsystem, it's important to note that we never abandoned the notion of particles. This cannot be done because we are within the realm of the Liouville equation. So we are talking about particles, corpuscles, but we are also talking about fields. Well, these are the two systems that we have. We have now a field subsystem constituting the electromagnetic field around the particle subsystem, and also the corpuscular subsystem or particle subsystem constituted by the electron and the particles in the nucleus, protons, neutrons, etc. In this case, of course, the field subsystem will function as a thermal reservoir. Instead of it, we will have our quantum mechanical description related to the particle part of our system, the particle corpuscular subsystem. This is why we have here the label X, which represents, in this approach, the position of the electrons. Of course, we are assuming that the nucleus here are fixed at the origin, etc. So if we look at the Schrödinger equation, what we find is two elements, important elements of the description: a potential that does not change despite the X can change, of course, and which is related to the field subsystem, and thus the thermal reservoir, and the particle or corpuscular subsystem, which is the main element of description. That is, our psi function refers to the corpuscular part of our entire system because it connects to itself to the particles by means of the X label here. So in this case, it's possible to assume that we have a type of mechanism in the atom. For instance, we are using here the example of the atom that may produce fluctuations in the following sense. We may have, for instance, I will draw the electron here just to be easier to draw the other elements. And we are, of course, assuming that this electron is interacting with the nucleus. But what means interacting here? Interacting here is to interact by electromagnetic force or electromagnetic field. But if we look at this electromagnetic field, we may assume that this force is real by photons. We may assume that we have photons being exchanged between the electron and the proton, either by sending these photons from the electron to the nucleus and backward by the nucleus to the electron. The fact is that these photons have finite velocity, the velocity of light. Then they take time to go from the one part of the corpuscular system to the other part. This means that if we look carefully at the mechanism of the interaction, we have a situation in which some photons emerge from the particle system, and this will make the energy of the electromagnetic part, the field, to increase because more photons are sending to the space where the field is defined, while the particle subsystem will have its energy lowered by the same amount. Of course, when this photon sent to the other part of the corpuscular system are absorbed by the electron or by the nucleus. The field energy is lowered, while the particle subsystem has its energy increased. The fact is that we have a large number of photons here, so we expect that the behavior of these two energies would be something like that. That is a fluctuation. This is how we interpret the origin of the fluctuation in any quantum mechanical system, because of course in any quantum mechanical system we will have these two elements, a field and of course a particle subsystem. In the next video I will show how this new interpretation helps us in understanding the whole of a single system interpretation in the realm of quantum mechanics. Thanks for watching.